Welcome to a video about limits in calculus. So we've been studying calculus this whole semester, and obviously things worked out, but there was a problem with calculus, right? So Newton invented his method of fluxions, but then didn't tell anybody about it, really just shared it with a couple people, but did show people the kinds of problems he could solve with it, which led to Leibniz reinventing it. Leibniz, who was a lawyer, who was an ambassador, who just picked up mathematics because of this cool Dutch scientist, Huygens, he met while he was in Paris, um, was able to kind of reconstruct what Newton had done from very little information. And so Newton had kind of very complicated structure for imagining. Mostly his fluxions he was thinking about change with respect to time. Leibniz took a more geometric approach. And because he shared it with people, you'll notice some of the notation here looks pretty close to what we've been doing um, in our class, right? So that notation was well adopted. So what's the problem, right? So the heart of the problem is that when we are first thinking rate of change, we were talking about it as slope. So we are imagining if you have a point that you want to know the slope at, you go a little farther down the line and you can calculate the slope. So that simplifies to this kind of expression, and we're thinking about it as, well, what happens when h gets infinitesimally small? Well, that doesn't necessarily make a lot of sense, right? Because um, we can't let it be HB0, because if we let H be 0, then we get 0 divided by 0, which is not helpful. But on the other hand, Newton and Leibniz and these early calculus pioneers knew that it worked, right? As you got closer and h got closer and closer to 0, often this expression gave them a specific value, and that matched exactly what their intuition should be for slope or for rate of change. Um, but not too long after the calculus was published, a bishop took issue with it, and he really constructed a pretty good argument criticizing what went wrong, what was wrong with the argument. And why the bishop cared about it was because Newton used the calculus to solve a lot of what were called mechanics problems, the physics of how planets moved and those sorts of things. And that led to people thinking that God wasn't involved in the universe, that it was kind of a clockwork universe, as what some people started saying. And so Bishop Berkeley wrote this critique where he referred to fluxions or infinitesimals as the ghosts of departed quantities, which is really a pretty clever and damning phrase, right? So, so if we think about this, right? So if we think about kind of one of our favorite derivatives, then we could look at it in this way and see kind of what happens, right? So we'd be saying f of x plus h is just squaring, and we subtract the f of x, and we're dividing by h, and that we do the expansion on this. And it simplifies down really nicely. So it's easy for us to say that, well, so as h goes to 0, this would be just 2x. And mathematicians were really pretty happy with this structure. Only over time did Bishop Berkeley's criticisms, and then people started proving some conflicting results. Although I've never been able to track down exactly what those are, but there were problems developing to the point where people were worried that if they couldn't kind of figure out a fix for calculus, we'd have to give it up as mathematics, right? Because contradictory results really doesn't fit in with what we want as mathematicians. So one of the where this really comes in is precision, right? So we were talking about infinitesimals and thinking about quantities as they tended towards zero, but we didn't have language for what does that mean exactly. So one of the first big ideas about how to fix this was this um, French mathematician with an Italian accent, Joseph Louis Lagrange. And his idea didn't work out, but later inspired some amazing mathematics. He thought about kind of defining functions in terms of their derivatives. You'd have a term that would kind of go for the kind of the numerical value, and then think about the change with the first derivative, multiplied by an x since that's slope, with the change with the second derivative, multiplied by x squared. And it turns out what he was thinking would work out, but people weren't happy with it because it meant really changing the way we thought about functions and how we write functions. And it was almost fixing the problem by doing an end run, saying, well, instead we're going to define the derivatives and we'll build our understanding of functions based on that. Um, and people also didn't like it because the infinitesimals kind of had this nice intuitive explanation that helped people understand what was going on with that. Um, don't worry about Lagrange. He went on and did a lot of great mathematics. And like I said, that idea really took hold. So often the person given credit for kind of fixing this problem is another French mathematician who was not very popular. So he was irascible, he didn't deal with people well. His professional disappointments he then kind of visited on other people. But if you kind of want to think about somebody to emphasize precision, Augustin Louis Cauchy is one of the uh, best people you can think. And so what we want to talk about is this idea of limits. That's what he invented to fix this. Now, to say he invented it, he was kind of part of a community of mathematicians who were talking about these ideas. In particular, Bolzano, his name comes up. Um, but we think that maybe he was kind of the first in a way, and then he also kind of published and really nailed the precision, right? So what he said was, what we really want to be able to do is we want to say that talk about this thing he constructed, the idea of a limit, and to say when x is getting close to some value, we want to say that the limit of this function as it gets close to that value is some number. All right, so I have an example here for us to think about. So this is the function sine x over x. Okay, so if we think about um, what is the function at 0, well, Desmos tells us it's undefined, and for good reason, because sine of 0 is 0, but x is obviously 0 when it's 0. So 0 divided by 0, this is one of these phrases, one of these things in math, we don't try to define what that is. It's just kind of out of bounds. There's no consistent way to define it where we wouldn't be unhappy with that definition somewhere else. But when we look at this graph, it has a limit. It's getting close to a number. It's close to 1 there, right? So, and we can see if we put in f of 0.1, well, we're already at 99 hundredths plus. If we do f of 0.01, well, now we've got 4 nines. F of 0.0001, we're almost running out of digits for nines, all right? So as we get closer, it's definitely getting closer and closer to 1. And we can see that even as we zoom in. right? Can't see a hole in it or anything, even though that point is undefined. So what Cauchy wants to say is that, well, we could talk about, even though f of 0 is undefined, we could talk about the limit as x goes to 0 of that sine x over x is equal to 1. And what he did was, what these mathematicians at the time did was really spell out, so what do we mean by that, right? We want to say it's getting close to that limit L when the x is close to our target value of a. So what we're saying is that the difference between f of x and L is small. This is the way we interpret that kind of getting close, right? Like we could say, well, how can we get it closer than 100th? Well, yeah, you just saw we could get it closer than 100th. So the question then is, well, how close does x have to be to guarantee it's less than 0.01? And so we have some very traditional language, so Greek letters we use for this. So kind of that condition of how close is the function, we say it's epsilon, which we're imagining as kind of small numbers. So we're saying that no matter how close we want to get to L, we can find some other number that will serve as a guarantee. So that if the x is close enough to a, less than this number that we find, then the function is going to be closer than whatever criteria we picked, like 0.01 or 0.001, or however close we want to pick. We can find a delta that guarantees the function is going to be closer than that. And what that did was it allowed mathematicians to be precise. So when we said this limit is going to this, it gave us something we could write down and saying, and what we mean by that is this inequality is true, right? And it gave us a way to prove that these things got close in a way that everybody could agree, like this is a good standard, this works. So here's an example. So I took the function x cubed. So if we set up that derivative limit for x cubed, it looks like kind of this top line. So we're saying that this difference as h goes to 0, despite the fact that technically we can't plug in h is equal to 0, that it gets closer and closer and closer to 3x squared, which is what we know we've been using all semester, the derivative of x cubed is. So the idea of these limit proofs goes something like this. So we pick an epsilon greater than 0. Then what we want is for this expression, the difference between our limit expression and what we say the limit is to be less than epsilon. If our h is close enough to 0, so we're going to try to find a delta that makes this guarantee work. So there's just a little bit of algebra here. We're writing out, kind of expanding out what x plus h cubed looks like. And then we can subtract, we get the x cubed minus the x cubed, so that cancels out. And then all the other terms have an h in it, so we can divide the h. Now it's tempting here to say, well, let's just let h be equal to 0. But we can't really do that because up here we were dividing by h. And dividing by 0 is not something we're allowed to do in math, right? So we can't now just switch gears and say, but now we could let h be 0, because previously we did something that doesn't allow h to be 0. So when we subtract the 3x squared, now this part cancels out, which that's good, right? Because when we look at this, we're thinking about h being a small number. So we could guarantee that this thing is small if we just thought that h was small enough. So I was thinking about it and thinking, well, it depends on x. So if it was just the h squared part, I could say let h be smaller than square root of epsilon, and then h squared would be epsilon, and we'd be almost there. Like, so we could just say it's half of square root of epsilon. Um, so, oh, I see a mistake I made in here when I wrote it out. Anyhow, it won't affect it be working out. But this other part, I had to think about, well, what I want is basically kind of 3xh to be less than half of what we've got there, which means that we want h to be less than kind of half of epsilon divided by 3x. So you'll notice this doesn't work if I want to say it works for all x's at once, because x can be an arbitrarily large point. What this does let me say, okay, well, if we pick an x, this technique I've got here will work. So we said delta is less than this, and we're saying that h is less than delta. So that means that this expression is less than if we plug in this, because delta is guaranteed to be less than this, right? If it's the square root of e is smaller, square root of epsilon is smaller, then then it would be smaller than this. And if it's equal to if this part is smaller, it'll be equal to this. And then what I realized I did wrong here was that 1/3 should actually be 1/9, because we squared that's 1/3 of square root of epsilon is squared. So this makes it messier than it had to be. But because this part on the left is less than half of epsilon, and the part on the right is less than half of epsilon, we get the whole thing is less than epsilon. So if our delta is this, and our h is less than delta, we're guaranteeing that this function is closer than epsilon to 3x squared. And that's what the limit means. So most calculus classes kind of start out with limits at the beginning, because this is now how mathematicians think about and define the function. And undoubtedly, as you read Professor Bolkin's book, you noticed this kind of limit language coming up in it. Why I don't do it too much then is because often, though, I feel like the way we teach limits is much like the kind of hand waving that Newton and Leibniz were doing. They said, well, we're imagining it does this, and we're dividing and canceling out, and kind of looking at trends and looking at graphs. And that's really what Newton and Leibniz were kind of doing at the beginning. But then this limit language came in as really a wonderful invention. It's kind of the start of analysis. When we think about kind of the branches of mathematics now, what was calculus is now kind of this field called analysis, right? So, and it's all concerned about kind of making these approximations and finding bounds and really getting into kind of the mechanics of how does this calculus stuff, and then the generalizations of calculus, how does that stuff work, right? Working out the details, being very, very precise. So despite what I showed you here, analysis was a lot of what I did when in my more mathematician-y days. So anyhow, and this language of limits fixed the problem that Bishop Berkeley pointed out about the ghosts of departed quantities, because they were no longer ghosts. Cauchy's limit language kind of brought them into the light and made them concrete and let us do more mathematics with them. And so they fixed the calculus, and math went on to solve many great problems with this material. So anyhow, I feel like that's a lot of the story of how limits saved calculus.